materials, and we are on kinetic theory, which I think actually is really, it might be, well, it might not be too bad. Okay. Right, let's start, if you can write that down. Kinetic model of gas. Got that? It's the something. 8, 9, something like that? 9, okay. Okay, you got that? Yep. Yep. So, yeah. So this is just a little bit of a reminder of something that you probably have written down already, I think, right? Pressure is force over area. We've discussed this, haven't we? Yeah. So there's nothing new there. What's the units for pressure? Pascals, yeah. Now, and we also say that 1 Pascal is the same as, what's 1 Pascal? Another unit for Pascal. Oh, do we not remember? A Pascal is the same as a... No. Nearly, you left one word out. That's what you just said. Newton per meter squared. Yeah. Okay. Now, we shall begin by imagining our gas, our ideal gas, to be like what we see in the picture below. So before I show you that, we just need to assume some things about gas. Now, in the exam, well, actually before that, okay. Have you done ideal gas in chemistry? Ideal gas? Have you done this in chemistry? No? What are you doing at the moment?
Balancing equations.
Okay. Have you ever heard of this, an ideal gas? Yeah. It's a particular type of gas which obeys formulas like PV equals nRT and things like this. So there's a couple of assumptions about this gas, and in the exam they sometimes ask you to give some of these assumptions, like to give 3 of them. So the assumptions we'll make about the gas is, number 1, the gas has a low density. So this is, we imagine the gas has a low density. Of number 2, colliding particles. So we imagine the gas as little particles that collide. Okay. Number 3, there's no attraction between the particles. So for example, it's not like some of the particles are positively charged and some are negative, or there's some kind of force pulling them together. So we say there's no attraction between the particles, they're just bouncing around. And 4, we ignore gravity in the gas. Okay, so it's not like we imagine all the particles fall to the ground. It's as if they're in space. So we imagine the gas as just being small balls bouncing around in a box with no gravity, basically, like in the picture here. This is how we picture the gas. So I need you to write down these 4 assumptions and draw this picture. You have this, Kim? Yeah. Siba? Yeah. George? Yeah. Chow? We can continue. Did you draw the picture as well? Show me. Show me this beautiful picture. Ah, yeah, that's not too bad. You drew the picture, Matt? Okay. Okay, good. All right. Continue. Yeah. So far for the exam, you need to know these basic assumptions about the ideal gas. So low density colliding particles, no attraction, ignoring gravity. These are some. They don't actually ask for all of them. You know, sometimes they ask for 2 of them, or usually 3 of them. Yeah. Now, let's see what formula we can make. So, the proof I'm about to show you is kind of on the exam. What I mean is, they don't ask you for the... Okay, so in the physics course there's, I think there's 3 proofs on the exam, and this is one of them. But because the proof is so long, they never ask for the full proof. They just ask a question that tests that you know the proof or you understand the proof. So they might ask you for part of it, okay? So you do need to know this proof. You do need to at least fully understand everything in the proof, because they may and they have tested students' knowledge of the proof by asking, you know, a question about a particular part of the proof, okay? So we won't go too fast, and if you don't understand something, it's important that you ask me, okay? So let's have a look at the proof now. So before we look at the full gas in the box, we'll keep it simple to begin with. We'll just look at a part of the box. We'll just look at one particle, okay? And what it does is, it comes along, it hits the wall, bounces off, you know, and then hits the other wall, and you're back at the start then. So just bouncing between the 2 walls, okay? And we'll say the distance here, we'll call that L, okay? And we'll say the time, we'll just call that delta T, okay? And at the beginning, it's heading in with a speed of V. Okay, so far? Right, so, and this is the wall of the container the gas is in. So we'll start by calculating the change in momentum. So first, it's going to be mv minus mu. Now, at the beginning, it's going with V, but after it bounces with the wall, what is its momentum afterwards? It's minus V is afterwards. Yeah. So the change in momentum will be mv minus mv. Oh, sorry, I wrote that backwards. The V here is actually minus V, and the U is actually V. So it comes out with V and goes in with V. So that's minus mv minus mv, so that is minus 2mv. Okay? Now the reason for the minus is because it hits the wall and it gets pushed to the left. Okay? What I actually want to know is how much force is felt out from the wall. So if that's delta P, if I divide by delta T, what have I just worked out according to Newton? That's the F. Because remember, F is delta P over delta T. Okay. Now, the reason that's a minus is because that's going to the left. It pushes the particle to the left when it hits the wall. It goes left. But I want to know what is the force that the container feels. So if I take that bottle there, so you understand that the water inside here is pushing out, that there's a force out here. That will equal the F here, just in the opposite direction. Which of Newton's laws is this? The third law, yeah. So the force on the wall will equal just 2mv over delta T. Okay, is that okay so far? Now I'll pause for a minute, I'll let you write this much down, and then we'll continue with the next part. Okay, you have that? Yeah? Now, let's simplify this a little bit. So, I don't really want the delta t here. If you look at this, what is the total distance the particle travelled in one sort of cycle? It travelled the distance of 2L. Okay, so if you think about your triangle, distance, speed, time, the distance is 2L, the speed is v, and the time is delta t, we'll call it. So delta t will equal 2L over v. Is that okay? Yeah? So now you can say the force on the wall is 2mv over 2L over v. So the 2's cancel, and the v comes up to the top. So you have mv squared over L. Is that okay? Yeah? Okay, next. You know, so I'll just go down to here. So I'll just put a mark here. So we continued, and this is like the second half now, or the next part. You know that force is pressure over area. Yeah? So here, this force here, oh sorry, I said that wrong, didn't I? Pressure is force over area. So that means force is pressure by area. So let me put that in. So the force on the wall is the same as the pressure on the wall by the area of the wall. That's equal to mv squared over L. What's the area of the wall? Well, we're calling if you look at the picture we had a moment ago, we're just saying everything is L to keep it straightforward. So what would be the area of the wall? L squared. Yeah? So you can now say that P, the pressure on the wall, by L squared equals mv squared over L. Yeah? Which means you can say that P equals mv squared over L cubed. Okay, I'll pause there and then we'll do the next part. Got that, Butch? Got that? Yeah? Okay. So we've just said that the pressure... Oh, sorry, Stephen, do you need it? You sure? That the pressure is mv squared over L cubed. Now, what is L cubed in this picture? What do you say L cubed is? Come on, don't be shy. The volume, isn't it? So this is equal to mv squared over volume. Okay, the next part. The small problem is, with our picture, the particle is just going like this, isn't it? Just left and right. But of course, if it's in a gas, it can be going in many directions. So we have to kind of fix that now. So imagine we have our particle and it's moving in x, in y, and in z. But I'll keep the speed the same. I'll say the speed is still v. Okay. What do we normally do in physics when we have a vector? We normally resolve it into the different components, right? So we can call this part v, we'll just call this vx, vy, and we'll call that vz. Yeah? Now, you know that Pythagoras, said vx squared plus vy squared plus vz squared, that's equal to v squared. It's actually Pythagoras, it's just in 3 dimensions. Okay. Now, vx squared will roughly equal vy squared, which will roughly equal vz squared. And we were actually looking at vx, because we were just looking at it going like this. Now, does anybody know why I'm actually saying these 3 are roughly equal? Well, consider if they weren't equal. What would happen to the gas if, say, Vy was bigger than Vx and Vz? What would happen to the gas? If all the particles had a Vy which was on average bigger than Vx and Vz, what would happen? What would the gas be doing? Be going up, wouldn't it? But because the gas is staying in the box, on average, the 3 directions have to be equal. Okay? So the Vy has to be on average 0. Sometimes it goes up, sometimes it goes down. Okay? But the size of it has to be equal to the others, because there can't be any preferred direction. Okay? So you could actually get this result, 3vx squared is roughly equal to the speed squared. So if I want to actually change this into 3 dimensions, all I have to do is divide it by 3. So I'll get 1/3 mv squared over volume. So if you want to be more particular, it's like in all the previous part, this was really just a vx. And now I actually do want to make it 3 dimensions. Okay, so I'll pause there and I'll continue. Oh, by the way, I'll give you an example. In the exam last year, I think they asked you, what is the purpose of the number 3 in the equation? So, why is it that I have the number 3 here? What was it about the situation that made the number 3 appear? Why was it a number 3? 3 dimension, yeah. If this gas was in 2 dimensions, then this number here would have been a 2, okay? So this is what I mean when I say they ask that you understand the proof. Yeah? I'll pause for a moment and let you write this much down. Scroll up. MV squared is negative? Yeah, I dropped the minus because I'm looking at the minus was because the wall is pushing the particles to the left. But I wanted to know what is the force the wall feels outwards, you know. Continue down? Yeah? Yeah? So we now so far have this formula. Pressure equals 1/3 m speed squared over, what was it? Over volume, wasn't it? Now, what I'll do is I'll just change this into 2/3 times a half. What's 2/3 times a half? It's, what is it? 1/3, which is actually the same thing as that. Now, can anybody see why I might want to make that little change? What have I achieved by doing that? Do you recognize anything in this formula? Yeah, kinetic energy. Okay, so you have pressure equals 2/3 times the kinetic energy over the volume. Yeah? So now you get pressure times volume equals 2/3 times the kinetic energy. Yeah? Now, in my proof, I only have one particle. But, of course, there's more than one particle. So, what change do you think I'll have to make here? This is the kinetic energy of one particle. This is the kinetic energy of one particle. If I had two particles, then the only thing that would change is, at the beginning, I would have like two collisions. So, it would be twice as much force and twice as much, like it'd just be 2 all the way down. So if I had n particles, what would happen to my formula here? What change would I have to make? Just times n, isn't it? 2/3 n times the kinetic energy. Okay? So this is just going to be the total kinetic energy. So I'll just write it as PV equals 2/3 total kinetic energy. Now, do these particles have any potential energy? No, because we said we don't consider gravity. So the kinetic energy is actually all the energy. There's no potential in it. So I can even change this into PV equals 2/3 times the energy of the gas. And now I arrive at my result after all that work. The energy is equal to 3/2 times the pressure times the volume. This is the energy in the gas, so to speak. It's like how much energy the gas has, By containing the gas into a container of a particular pressure and a particular volume, you've worked out how much energy it has. Yeah.
What's the last one? E?
Gas. did you write that down? Yeah? Got that? So, just to be completely clear, this is basically what I'm saying. Imagine you had a very large room, like really large. And we'd say that the volume is, quite big, so we imagine it being, like infinitely big. Of course it's not, but you know what I mean, like really large volume. And we'd say that the pressure is quite low, so the pressure is about 0 pascals. Okay, so it's big and there's not much gas around. And then you take the gas from this and you put it into a small container, where the volume is a small number and the pressure is kind of a large number, large enough. How much work is done? Well, the work done is given it the energy it needs, which is, what did I say, 3 over 2? 3 over 2, 2 over 3 PV. Okay, so it's kind of like the energy you need to nearly make a container of gas with a particular pressure and volume. Okay, so I think it would be good for you just to draw this picture as well, and then that's the end of the proof.
So I finished?
No, that is the end now. I thought it was 2 over 3. That's what. Oh.
Sorry.
Oh man. Alright, 3 over 2. It's 3 over 2. Got that? Got that? Yeah? Okay. So 3 over 2 PV, that's what we said. Now what I think that makes this so interesting, like really if you really think about it, what makes this so interesting is that it's quite easy to find the pressure and the volume, isn't it? Like volume you just measure, and the pressure you can measure as well. But you can know something which is very difficult to find. Like if I said to you, find the kinetic energy of 1 billion particles in a gas, you couldn't do that. It's impossible. Now, how on earth could you do that? But you could measure pressure and volume. And by measuring these big things, you can know about this small thing. Like this is what I think is so interesting about it. You can know the energy, all the kinetic energy of all the particles by measuring the pressure and the volume of the gas. Yeah? Maybe this means more to me than it does to you. But it is quite interesting, I think. Alright. Now, it may seem like we know how much work is done to get a gas when we change its pressure or volume. However, this tells us the stored energy in the gas and not the work done to distort the gas. Let's calculate. So what I mean by that is, if I can take this again, yeah, sorry. There's 2 types of work you can be doing, okay? The first work is to get the gas into the container to begin with. Okay, that's what we've just calculated. That's the 3/2 PV. Yeah? That's not the same thing as the work done to change the pressure or the volume. Okay? So if I squeeze this container, what am I doing? I'm changing the pressure and the volume, right? The formula for working out the work in my hand is not the same as how much work it was to get the gas into the container. That's a different thing altogether. You know, it's a bit like, you know, you might have to do some work to make a spring, but that's not going to be the same equation as the work done to change the size of the spring. You understand? Like, it's two different situations. So we want to have a look now at a shorter proof. Don't worry, it's only a couple of lines. How much work is done if you were to change something about the gas. Okay, so let's see. So let's like the normal situation is you imagine you have some container like this, and it contains a gas that has a pressure and a volume. And then what you do is perhaps you have this connected to some machine and you push down on it. You apply a force. Okay? And we'll say that this is a height h and a radius r, just to keep it simple. Okay? Now, work done. You know what that is from the definition. Like, what's the definition of work? Like, what's the formula for work? Force times distance. Okay? So we need to know a distance. So let's imagine we just push it down a small distance. I'll just call it d here. So that's F times d. Okay. Force, if you remember, pressure is force over area. Force is pressure by area. Okay, so that would be PAD. Okay, so far? Yeah. So that is yeah, no, that's just PAD. But I kind of don't want to have the D in it. How can I best put this? Yes, okay, I'll try this. P pi r squared, that's the A. Now I want a formula for the D. Okay, so if you think about it, it starts off with volume V, and then it gets a smaller volume. So I'll say it goes from V1 to a smaller V2. Yes? Is that okay so far? So V1 minus V2, what would that equal in my picture? So imagine it goes from here down to here. What's V1 minus V2? Nearly, yeah, it's actually the volume caused by D. Yeah? So that would equal pi r squared d, the volume of this small cylinder. And you can actually call that delta V if you like. That's the letter, the small volume. So let me see, that's equal to P pi r squared, and the D is delta V over pi r squared. So the pi r squareds cancel. So I'm left with my result. The work done is equal to the pressure times the change in the volume. Now, this proof only works if you assume that the pressure is constant, which isn't really very accurate, because what would you imagine happens to the pressure if you were to shrink the container down? What do you think happens to the pressure? Increases, doesn't it? So it doesn't really work if the pressure changes a lot, only if it changes a little bit. So you can only really use this if you want to calculate a little bit of work done, just a small change in the height. Okay. So the work done is the pressure times the change in the volume. This is if you like reduce the volume a little bit. Okay. So not as difficult as the last proof. If you can write this down, please. Yeah, go ahead. Got that? Yeah. Continue. Continue. Tired, sleeper? Tired? Are you sure? What time did you go to sleep at?
3.
Oh, Sivan. What were you doing up until 3?
Watching streams.
Netflix? No. YouTube? Okay. 3 o'clock? What time did you wake up at?
7.
That's not a lot of sleep. Not a lot of sleep. That's like how much sleep Kim gets, you know. Yeah, can you get by? Okay. Right, can I scroll down? Yeah. Well, let's actually see. So we have our formula here. Okay. Promise you this is the last proof. So next we're going to look at the pressure on, I said a sphere, but perhaps I should have said a disc here. So, let's see. Yeah, no, I need to do the proof. Okay. Right. Next now. So the third and final formula for this lesson. We probably know this already from our experience that the further underwater you are, the greater the pressure on your body. You know this from experience. But it doesn't have to be water, it could be a gas. You know, the deeper into the gas you are, the more pressure there is on you. Okay? It's just we don't obviously go swimming in gas, so we don't really notice it. Okay? So we want to figure out what is the pressure on, let's say, a circular disc. And we'll say it's at a depth of H. Okay? And we'll say the gas or the liquid has a density rho. Okay. So let's calculate the pressure here. It's not actually that difficult because you can just say the pressure is the force over the area, and the area will be pi r squared if you say it's a radius r. But what's the force? What actually is pushing on this disc? It's maybe hard to see. Any ideas? Not its mass, but some mass. Can you imagine? It's like all the water that's above it in this column of water is pushing on it. That's why it has a force. So it's actually the weight of the liquid. But the formula for weight is mg. Now we don't know the mass of this, do we? But we know that density is mass over volume. So mass is density by volume. So that's density volume g over pi r squared. Okay, well, what is the volume? What's the volume of this cylinder? It's pi r squared h times density times g over pi r squared. Now, the pi r squareds cancel and you're left with rho g h. That's the pressure. But what's interesting about this is the radius has disappeared from the formula. So that means the radius is not important for the pressure. So you could now make the radius 0 and just make it a point. So the pressure at a point is given by this formula. In other words, you don't need to know the shape of the object to know how much pressure is on it. You just need to know how deep it is, the density of the liquid, and G. Okay, if you can write this proof down. Okay, Siba? What's so funny?
I drew the photo too small.
Oh, okay. Alright, you got that? Now, the next thing I want to tell you is actually, if you think about it, you're in a gas right now. You know, because here you are on the Earth, and you're actually in, what is it, 70% nitrogen, something like this? 75% nitrogen, 25% oxygen, something like this. So you're actually at the bottom of like an ocean of nitrogen. So there's going to be a pressure on you. Just like how in the previous example we had a pressure. This pressure, we call it 1 atmosphere of pressure. And it's actually a pretty big number. It's 1 atmosphere of pressure is 101 kilopascals. Now, think about how big that is. That means for you, the pressure on your body is 101 325 newtons per meter squared. Okay? I mean, goodness, that's like having that. Imagine you're lying on the ground and you had 100 people standing on top of you. That's how much pressure it is. Now, you don't feel that, right? Is there a reason why we don't feel it? Because we constantly live with this. We don't, no creature is going to exist feeling this because it's around us all the time. But it's quite amazing when you think about it. The force on your body is as if there was 100 people standing on you. That makes you sound pretty tough, doesn't it? Like, it is really that big. Okay, like the pressure, because, think about it, there's a lot of sky above you, so there's a lot of gas pushing down on you. So 101 kilonewtons is quite a lot of force per meter squared. So you'll need to note this. Now, I should say this value changes, of course. So, like, for example, if you climb up to the top of a mountain, is the pressure greater or smaller?
Smaller.
Yeah, because there's less air above you. Okay, and likewise, if you were to go to the bottom of a valley, it would be greater. So we say on average it's 1 atmosphere. Also, the weather affects it. If a day like today, would it be more or less pressure, do you think? If you think about the news, if you listen to the weather, what happens when the weather goes bad? What happens to the pressure? Do they say the pressure goes up or goes down? You watch the weather, don't you? Or no? No? Okay. Pressure, do you mind getting that? Matt's got it there. The pressure goes down on a day like today. And when it's nice and sunny, the pressure goes up. Yeah? You never noticed this? No? No? You know those things you see in homes that look like clocks? They're called barometers, and they tell you if it's going to be raining or sunny. Have you ever seen those? Are you sure? This is a cultural thing? You know what? No? You have never seen this? It looks like a clock, and it says if it's going to be sunny or rainy, and it's hanging up by the front door. Do you know it?
I think I've seen it before. It's wrong, but it doesn't have. It just looks weird.
It just looks weird?
Yeah. Looks like a clock, but it's weird.
Yeah, it looks like a clock.
Yeah.
Okay. You've never seen this?
There's a ring buckle.
Perhaps that's why. Kim, have you ever seen anything like this? No? No. Okay. The way it works is it measures the pressure. So if the pressure is high, then it's going to be a sunny day. And if the pressure goes low, then it's going to be a rainy day. So that's how it predicts the weather for the day. But this is a cultural thing. You haven't seen
But
this.
why is the pressure higher when it's sunny?
I'm not sure, because this is more weather science, which I don't know about. I think it's. I was just going to say. I think it's because when the air gets heated, it expands, so it has a more downward pressure on you, perhaps. I'm not sure actually. I'll have to check it to be certain. So you need to know this value, 1 atmosphere of pressure. That should be a small k actually, kilopascals, so small k. Okay, you got that value? Yep. Right. Here's an example. We'll do this together. What pressure do you feel when you swim 5 meters below the sea? So, if we use our formula, pressure equals rho GH. What's the density of seawater, salt water? What do we say it was? 1,015, was it? Something like that, wasn't it? 1,030. And the G? 9.81. And how far under? We're 5 meters under. Okay, can you tell me what this is? How many pascals of pressure is this?
50521.5.
505.
0521.5.
Yeah. So that's 50.5 kilopascals.
They have to submit the answer in kilopascal.
It's strange, but I mean, it's fine for the exam if you don't, but
It really doesn't matter.
pressure is normally measured in kilopascals on weather and things like this. Yeah. Next example, you got that? Yeah?
What is E? Oh.
E?
That.
Oh, E? Where's E? No? Okay. Okay.
Sorry.
How thick is the Earth's atmosphere? How thick is the Earth's atmosphere? So, that's an interesting one. But you can work it out, because if you think about it, here you are here at the bottom, and here's the atmosphere, and it has a height h. Okay? And you want to know how big is this height. In other words, how far could you go until you can't breathe anymore? What's the distance? Right, so let's calculate it. If we think about our formula, pressure equals rho GH. Do we know the pressure? We do. It's 1 atmosphere when you're at the ground. Okay? Do we know the density of air? I think I gave you that in a previous lesson. No, don't look it up, because I remember it. It's roughly 1 kilogram per meter cubed. It's actually a little bit more, so it's roughly 1 kilogram. The G, do we know? Yeah, and the H is what we want. The H is, so it'd be P over rho G. So that's 101,325. Is that what I said it was? The atmosphere?
Mm-hmm.
Yeah. Now, I think it's something like, it's roughly 1, but I think I'll be a bit more accurate. I'll say it's 1.3. No, what am I doing? I don't know what it is. I'll just say it's roughly 1. And the G is 9.81. Okay? No, don't type it in, because we're only estimating. We're only estimating. So this is roughly 10,0000 over 10. Like roughly. It's quite close to this. So that's 1, 2, 3. So that's roughly 10 kilometers. That seems like a pretty good estimate. If you think about it, when you travel up 10 kilometers, like in an airplane, you don't really have much air, but you still have air. So this isn't quite accurate. The reason it's not quite accurate is because we kind of assume that the gas is constant. Now, if you take the water for example, that's a reasonable assumption to make about water, because the density should be the same up here and down here. It's not like it's thicker here and thinner here. But this isn't really the case with air, because the planet, it's so big, it affects the air. When you move out, what happens to the density of the air? It doesn't stay constant. What happens to the density of the air? Do you get more air or do you get less air? You get less, yeah. So, this H here, you know, it's not like you go from, you know, a density and the density is the same. It's more like, kind of like this. You go density is quite big, then it's kind of in the middle, and then out here you actually have no density. The air is kind of disappearing. So this is more like an average rather than the limit. So if this is more like an average height, if I want the limit, I think what a good estimate is I could just make it twice as big. You know, if I say the average is 10, then the limit I think would be 20. Why don't you Google how thick is the Earth's atmosphere? Now, it has many layers. I'm just talking about the lower levels, the level that we live in. How thick is that? I think you should hopefully get something close to 20 kilometers.
How thick is the what?
Earth's atmosphere.
16 kilometers.
Yeah, 16 kilometers, okay. You got that? So I don't think we did a bad job. We estimated it to be 20 kilometers, and the actual answer is 16. That's really impressive if you think about it, because I only used one measurement, the atmosphere pressure at ground level, which you can actually measure on your phone. I think a lot of phones you can download an app to measure the pressure in the room. Yeah.
I know in the atmosphere.
Is there an app for measuring pressure?
Yeah. 991.
Oh, you have it on your phone already? Okay, can you change the unit to kilopascal? Is there a way to change the unit?
It's good setting and
I'll just put it into Google. Yeah. Yeah. It should be 101.3 kilopascals, but I'm going to predict it's going to be...
99.1
Yeah.
kilopascal.
I didn't get a chance to predict. What is it, 99?
0.1.
Okay. That's actually quite a bit less. So, it should be 101, and it's 99.1. So that's 2 kilopascals less because of the weather. Isn't it? 99.1, 100.1, 101. Yeah, because it's cloudy, it's dropped by a whole 2 kilopascals. You know, that's quite significant. Okay. So don't you feel a little bit lighter with the 2 kilopascals less of pressure on you?
colder.
No?
Colder.
Feel colder, though. Yeah. Okay. Right. So, I'll let you try these questions for a few minutes now. Yeah. Oh, battery's gonna go.
Yeah, I was gonna say earlier now. Winter.